to what's going on, how you're taking a limit to infinity, now's the time to check in. Let me quickly take roll. Thomas isn't an AP Bio, is he? Oh, he is. Didn't realize. Where's Colby? And Andrew's AP Bio. Is Toby in AP Bio? Okay. All right. Here's some guys over to the side talking about multiplying top and bottom by 1 over x squared. So you end up with the limit as x approaches negative infinity of 3 plus 1 over x squared all over 4 minus 5 over x squared. Joseph, what were you saying about every component where you have a constant over x to a power as you go to infinity or negative infinity? Approaches 0. Approaches 0. So the end behavior of this function, what's going to happen as x decreases without bound going to negative infinity? Well, you're just going to end up stabilizing towards, converging to 3/4. What degree test would have also gotten you there? Remember? Chapter 2? We didn't totally review all the degree tests, but we're going to today. And you guys could have looked back in chapter 2. What degree test would have gotten you the exact same answer of 3/4? Who wins? I don't know if I'd say neither. But yeah, the top doesn't win, the bottom doesn't win. There is a tie as far as the degrees. And so what do we do anytime there's a tie? No one looked back to chapter 2? What do we do when there's a tie? Ratio of, really? In honors? Come on, where are you? The ratio of leading coefficients. The ratio of the leading coefficients. So we would have gone ahead and looked at this guy and said, okay, let me grab out a highlighter real fast. Highlighter, there he is. That's the leading, the terms, or the terms that are greatest in their degree or greatest in their power. And so 3 over 4, dun, 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 dun. But the algebraic way also works and is a bit more precise, because as soon as we get over to this example, well, things get a little bit exciting. I'm going to change this example just a little bit, just to have it be a little more interesting, because right now it's a little boring. But don't worry, whatever you guys thought about, it'll still be almost as applicable. I'm just going to change this to be 3x to the 6th power and make this x cubed. We're changing it just a little bit. Make the bottom one the square root of 10 plus x to the 6th power, and the top one 4x cubed. Okay. Horizontal asymptotes. Horizontal asymptotes are talking about the end behavior of a function. And we talked about this way back in chapter 2. Horizontal asymptotes, the end behavior of the function. Question, what direction is the end of a graph? Where's its end? Where do we look? Where's the end? Take a parabola. Where's its end? Show it to me. No, that's the parabola. Where's its end, though? Point to a direction. Where's the end? Up? Kind of. But when does it get to the end? Where does it get to the end? As you go to the right? So it's going to be up there. And then as you go to the left. Now, does it end? No. but where are its ends? That way, right? But for a different function, say a cubic, where are its ends? Well, one's to the right and up, and the other's to the left and... Okay, so if I'm trying to say where, sometimes it'll be up, sometimes it'll be up and down, sometimes it'll be down, right? Sometimes it'll be like weird and maybe, ooh, like a circle held within, so it doesn't really go forever. But where do we go to get to the ends? We go to the right and we go to the left. How do we go to the right? We take a limit as x approaches positive infinity. And how do we go to the left? We take a limit as x approaches. How do we go to the left? Negative infinity. So to go to the right, to go to the left, some of that terminology that we used back in chapter 1 or 2, we have to go or take the limit as x approaches positive infinity or as x approaches negative infinity. So this is still answering the question of how to find the horizontal asymptotes of the given function. Now, let's use the process that we were talking about right over here. Okay? So what are we going to multiply top and bottom by? Come on, we did yeah, the square root. We did an example like this on Friday. 1 over the square root of x to the 6th. Because we need a square root in order to be able to bring it into the square root function. We're going to do that same for top and bottom, for the top limit and for the bottom limit. Okay, now in the numerator, we're going to get 4x cubed all over the absolute value of x cubed. Wait, what? How'd I get that? The square root of x to the 6th. Isn't that like a perfect pairing in the sense of I could say that this is x cubed times x cubed? So I could take the square root, but the problem is anytime you take the square root of an even-powered x, by definition, the absolute value is in there because this would be a positive, so I need this expression to always be positive as well. In the bottom, I'm going to get the square root of 10 over x to the 6th plus 3. Because I can bring this square root of x to the 6th into the square root because of the properties of square roots. 10 will end up over 3x to the 6th over x to the 6th will reduce to just be 3. Now, what did I just do that was horribly wrong? I stopped writing. Okay, well that's horribly wrong. Let me get this in so that I have some more room. Move my little baby equal sign. I can technically do the exact same thing down here. The limit as x approaches negative infinity. The simplifying is the exact same. I have 4x cubed all over the absolute value of x cubed all over the square root of 10 over x to the 6th plus 3. Here's where it gets a little funny. Joe, coming back to you. What can I make go to 0 right now? Anything else? To go to 0. What do you guys think? Can anything else go to 0? I don't have any other constants over variables. I have 4x cubed over the absolute value of x cubed. So where does this leave us? This leaves us on this guy at the limit as x goes to positive infinity of 4x cubed all over absolute value x cubed all over the square root of 3. And this guy, the limit as x approaches negative infinity, 4x cubed over the absolute value of x cubed all over square root of 3. Are you guys twitching just a little bit because you see x cubes over x cubes? Is it a little like, I just want to cancel them out? Why can't I quite cancel it out? The absolute value is getting them stuck. I could go writing this whole piecewise definition of absolute value functions. I totally could. And I could say, all right, the absolute value of x cubed is equal to, sometimes it stays the same, and sometimes it's the opposite. It's going to stay the same as long as this expression is going to be x cubed greater than 0, which means x greater than 0. But it's going to need to flip signs if x is a negative number being plugged into that. So I could do that, and I could say, okay, little absolute value of x cubed. If I'm talking about negative numbers, you better be the opposite. If I'm talking about positive numbers, you better be x cubed. Wait a minute. Hold on. Where am I approaching in this one? Positive infinity. Well, which one am I talking about? X cubed stays the same or x cubed flips? Stays the same. Positive numbers cubed are going to still be positive. So couldn't I kind of make this the limit as x goes to infinity of 4x cubed over x cubed all over root 3 and say, ha-ha, you guys reduce, so I get 4 over root 3? But what's going to be different on this guy? I'm going to negative infinity, so what's going to happen to all my absolute value of x cubes? They're going to flip. What can I now do with my x cubes? But what's left? Can you guys graph this function for me? 4x cubed over the square root of 10 plus 3x to the 6th, and try to figure out how on earth are there two different horizontal asymptotes, one at positive 4 over rad 3 and one at negative 4 over rad 3? Have we ever seen a guy with two horizontal asymptotes? I'm going to write the answer all nice and pretty while you guys are doing that. Two horizontal asymptotes, one at positive 4 over rad 3 and one at negative 4 over rad 3, which, just for sake of reference, we might want to get a decimal of so that we can go ahead and see what's going on. I'm going to go check this guy out. So it's 4 over rad 3. 2.309 something, so 2.3-ish. All right, let's graph them. Oh, my window is definitely not in Zoom standard. Hold on. It's a little funky guy. He has like a plateau in the middle. Anyway, let's see. What happens as we go to 5, or as we go to 6, or as we go to 7, or as we go to, I'm just on the trace feature, by the way, you can type in stuff. As we go to 8. It's closer and closer and closer to 4. Hold on. Oh, I didn't write in my, do 10 plus x to the, you guys should be getting closer and closer to 2.3-ish. Three. Okay, now let's try. Trace as I plug in 5 or 6 or 7. Hey, there's my 2.309. You guys see it? But what goes on if you go the other direction, if you are now doing negative 5 and then negative 6? Now, if I made my window bigger, I could go to negative 50, negative 100. I just don't want to stress with my window. But what's it seem to be approaching? So it's possible for a function to have more than one horizontal asymptote, and technically without this procedure of finding a limit to infinity or negative infinity by multiplying by 1 over, we wouldn't have really seen both answers. So think through with me. Hold on. Is there a shortcut way? Because the shortcuts are the degree tests. Is there a shortcut way? It's dangerous, but there still is one. A shortcut way to figure out 4 over rad 3 from the beginning expression without doing this crazy limit process. What's the shortcut? How could we have figured out 4 over rad 3? Now the whole plus or minus thing is going to be where it gets dangerous, but how could we have figured out the whole 4 over rad 3 part from the beginning? What's the strongest part of the top? There only is one part, right? The whole thing, 4x cubed. What's the strongest part of the bottom? But what do we have to remember is on the outside? What would be the ratio of the leading coefficients as long as we don't forget the square root? Wait a minute, we can't. They're not tied. The bottom wins. Wait. What would be the degree? Now, you can't actually distribute a square root. Totally illegal. Totally false. We can't simplify that because we'd be killing the poor, where is he? The poor little puppy. We can't do that. That's totally illegal. But what we can do is say, wait, it's a 6th degree polynomial under a square root. What would be the overall power of a 6th degree polynomial under a square root? Pause. Does it make sense to be a cubed? X cubed times x cubed would be x to the 6th, or x to the 6th square rooted would be x cubed. So can't I say this is indeed a tie? And what do we do with ties? Oh, that's right. Ratio of the leading coefficients, just don't forget the square root. Do you guys see your 4 over rad 3? Now what's the danger? Don't we need the plus or the minus? And that's not always true. The example that you guys had written down the first time, which was with an x squared on top and an x to the 4th down bottom, that wouldn't have given you 2 answers. That would have only given you 1 answer because an x squared is always positive. There is no opportunity for an x squared, unlike an x cubed, to change signs. So some of you might be like, wait, I think I can make a little rule out of that and actually not have to do any of this work. That's cool. We're going to try and do that. But if worse comes to worse and you guys are making mistakes, we'll come back to the math and say, wait a minute, do you understand why we need a positive and a negative? Absolute value behaves 2 different ways. Let's go to our shortcut degree test, because our goal is to be able to not have to show this work every time. But that problem that we just did is super dangerous. It's super dangerous to not forget the square root in your denominator, and it's super dangerous because of the plus or minus. So it's dangerous in lots of ways. And if it were to show up as a multiple choice question on an AP calculus exam, it'd be super sad if you kind of got the idea, but you couldn't get it right. Let's fill in the degree test really, really quickly, and then you guys can bust out those examples on the next page without having to show the whole multiply top and bottom by, hopefully without having to show the whole multiply top and bottom by the highest degree. Kiddos, if the top wins, right? P of x over q of x. You're welcome. If the top wins, who reviewed these? What happens? If the top wins, is the whole function being held back at all, or is it able just to expand, increase, or decrease without bound? It's able to increase and decrease without bound. If the top wins, it's just going to be ever increasing or ever decreasing. So therefore, wait, if it's ever increasing, ever decreasing, is it ever being held back to getting closer and closer and closer to a certain y value? No. So we'll say, first of all, no horizontal asymptote. That's what we first studied in chapter 2. And the reason is, we put a little double-sided arrow. Because the limit as x goes to infinity of f of x I should say and. The limit as x goes to negative infinity of f of x as long as the domain allows for both. Equal, I'm going to put plus or minus infinity. I can't really tell you which one. It depends on the function. Sometimes going to the right, it will go up. Sometimes going to the right, it will go down. Sometimes going to the left, it will go up. And sometimes going to the left, it will go down. But somehow, to the left and the right, somehow it's going to positive or negative infinity. If the top wins, it's not being held back at all. If there's a tie, remember, in the degrees, if there's a tie, we already talked about this one. There is a horizontal asymptote at y equals, I'll say L, at y equals L. I'm not going to put that. I'll do this. At y equals the limit as x goes to infinity of f of x and or the limit as x goes to negative infinity of f of x. Sometimes they both equal the exact same thing, so you only have one horizontal asymptote. Sometimes they equal two very different things, so you have two horizontal asymptotes. And sometimes one of them doesn't even exist, so maybe you only have one, but only coming at it or going towards one side. And we'll say these are going to be plus or minus. We have to be careful with the plus or minuses, especially with the weird square rooty thing like we just saw. But plus or minus the ratio of the leading coefficients. At plus or minus the ratio of the leading coefficients. Last but not least, two wins. Bottom. If the bottom wins, there's going to be a horizontal asymptote at y equals the limit as x goes to infinity, and I should put or the limit as x approaches negative infinity, which will be 0. So the first one, top wins, no horizontal asymptote because the limits are going to equal as you go to the right, to the left, to infinity, to negative infinity will somehow be infinite. Not getting closer and closer to a number, no horizontal asymptote. Second and third ones, both of them have horizontal asymptotes because the limits exist in equal constants. If there's a tie, ratio of the leading coefficient, but I'm going to quickly highlight the plus or minus because that's something we're going to have to check for and be careful for functions now than we did in chapter 2. With absolute values, with square roots, with other radicals, with more involved functions, etc. So we have to be careful about that whole plus or minus. We might have to do a little bit of investigation to figure out which one. And then bottom wins 0. So kiddos, check out number 11 over here. Let's go fast, even though we could do the whole multiply top and bottom by the 1 over the leading or the highest degree of x. If you just check this guy out, limit as x goes to positive infinity of 1 minus x over 1 plus x. What camp? Top wins, tie, bottom wins. Tie. What's the ratio of leading coefficients? -1. Oh no, the plus or minus thing. Is it not well behaved? Oh no, it's fine. It's okay. I mean, you could try even plugging in if you would like to test it real quick. It'd be 1 minus positive infinity all over 1 plus positive infinity. This is dangerous. This is fuzzy math. You would even need to put like little quotations if you actually ever put that anywhere. But in your thinking, this top expression is going to be negative as this is ever increasing. The negative numbers win. Down here, positive numbers are all that you're going to get out. So negative numbers over positive numbers. What's a negative over a positive? Which is why I keep the -1. But he was well behaved. Exactly what you would have thought just by taking the coefficient of the negative x over the coefficient of the positive x. How about number 18? What camp? Top wins, bottom wins, tie. Top wins. None. No, 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 no. There's an answer. Horizontal asymptotes would be none. But there is an answer. We put an infinity and we put a quick plus or minus to check. We put in an infinity, a quick plus or minus to check. It can't be both. It's impossible to be both. But we can come over here and say, okay, hold on, let's think about it. Guys, what are all the numerators going to be? If you plug in any, well, actually, any positive or negative. If you raise it to the fourth power, what's that going to have as its sign? How about the denominator? Positive or negative squared, still positive. Plus 3 is still positive. Well, what's a positive over a positive? Sweet. So we go off to the side, we consider the sign, we come back and say, booyah, we got it. Your turn. Ready, set, go. Number 27. Hint, you're going to have to do it in pieces. You're going to have to do the first little expression and the second little expression. So if you want to, you can think of it as, not that you have to write it, but you can if it would help. You could split up the limits and consider them separately. And then put them together with a minus at the end. I'll give you a second. We're not distributing the limit. That's not technically what's going on. It's not multiplication. But you can think about it as properties of limits. You are allowed to take the limits piece by piece. Let me get some air in here. It's a little bit warm. Give you guys a couple more seconds to ponder. Check in your groups real fast. Do they agree with what you did? All right, what case is going on for the first piece? Bottom wins. So therefore, what's this entire expression going to approach? Good. Minus. What's the second case? It's a tie. Oh no, plus or minus. Wait, think about it. Hold on, if you think off to the side, if I plug in 5 times a positive number, wouldn't that be positive? Even if they're getting bigger and bigger? How about bigger and bigger positives plus 2? Aren't they still positive? Okay, so the natural 5 over 1? Yeah, good. But it's 0 minus 5. 0 minus a positive 5, which will be negative 5. Dun, 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 dun. Dun, dun. So what if I was to give you one more? Do I already have a good one? I don't know what number to make it, so we'll just say my example. One more. The limit as x approaches negative infinity of five 7x all over the square root of 3 minus 4x squared. Take a second, consider the cases, try to do it without having to think about multiplying by 1 over the highest power and think about absolute values and all that yuckiness. What case would you put it under? What kind of answer should you have? What should you double check? Let's see if you can get all the way there. Then I want you to graph it and see if what you think is going on is actually going on. Did you graph the first one yet and see if what you thought was going on was actually going on? There's a struggle with the first one. There's a struggle with the first one. Did anybody think of degrees tied? Yes. Good. So you thought ratio of leading coefficients? Good. Did you think of 7 over negative 2? Good. Did you consider, wait a minute, hold on. Actually, if you plug in a negative, it'll be a negative over a positive. So negative 7 over negative 2 would be positive 7 over 2. But did you look at your graph and realize the domain is restricted, so x cannot possibly even go to negative infinity? This little square root would never let x's go to negative infinity, because if x's kept growing and growing and growing and growing, wouldn't it be square root of negative 4? And is the square root of negative 4 negative 2? It's imaginary. So some of you thought really, 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 really good things. The problem is x is not allowed to go to infinity or negative infinity. This function is closed in and will never expand to the right or to the left. Poor little guy. His growth is stunted. But take all the things that you thought about for the first one and apply it to the second one, because the second one is legal. The second one does not have a restricted domain. The second one, this expression under the square root will never equal imaginary numbers or 0. So we're okay now. So now take all the things you already thought about. Degrees are what? Tied. I'll put up here domain problem. Domain problem. This is not allowed. Okay, so degrees tied. Ratio of leading coefficient, 7 over square root of 4, plus or minus. Okay, let's consider the plus or minuses. What happens if you plug in negative, bigger and bigger negative numbers to the numerator? What kind of sign will you have? Negative. What if you plug in bigger and bigger negative numbers to the denominator, which gets squared and times 4 and adding 9 and then square rooted? Positive. So what sign do I have to use? The final answer is 7 over 2 with a negative. The final answer is 7 over 2 with a negative. Ryan?
Why do you, or how do you decide what sign to use again? Because
you have to, in a sense, without using what we did at the beginning of class with multiplying by 1 over the square root of x squared, realizing that's an absolute value, realizing absolute values are sometimes positive, sometimes negative, figure out for which this negative infinity would apply. The easier way is to visualize plugging in a really big number like negative 1,000. If the idea of plugging in negative infinity is too confusing, or negative larger and larger numbers is too confusing, plugging in negative 1,000 and saying, oh, 7 times any negative will always be a negative. And on the denominator, 4 times, well, negative 1,000 squared will be positive, times 4 will be positive, plus 9 will be positive, square rooted will be positive. So any negatives over positives will always end up being negative. Okay, last page. Last page for section 12.4, and I think we'll be able to start 12.5. Says, hey, you can apply this whole idea of taking limits to infinity with sequences. You can take the limit of the nth terms. Because remember, some sequences, not series, we're not going there, that's Calc BC, but sequences separated by commas. Sequences can go on forever. And since we can't get to forever, we could take a limit as n goes to infinity of the sequence and try to figure out what's happening. And the cool thing is we can say the sequence converges or diverges based on what we see from the limit. And so they're basically just saying, hey, apply this whole limit to infinity thing, but instead of using x, use n. And instead of taking f of x's, take these a sub n's like we worked with a while ago, and just see what happens. If the limit of the terms are 0, sweet, we'll say the sequence converges. If the limit of the terms are not 0, we say the sequence diverges. Although I don't really like that. My Calc BC teacher self doesn't like that, so let me just double check. But you guys can start with the examples down below, taking limits to infinity. Thinking of degree tests. Okay, hold on. I need to change this. Guys, change this real quick. I don't like how I worded that. We're still going to keep the converging and diverging thing, but we need to get rid of this specifically. Don't worry, most of it's the same. The limit as n goes to infinity of a sub n is a unique number It can technically be as the sequence will converge as long as the limit as n goes to infinity of a sub n is any unique number. It could be 0, could be 1, could be 4. But the limit is going to, or I should say the sequence is going to diverge if the limit is either infinite or bounces back and forth between different values, never converging to a single unique number. That's a better way of putting it. Or I should say that's a true way of putting it. So down here, when you guys were looking at the first one, what's the limit as n goes to infinity of a sub n if a sub n is equal to 2n plus 1 over n plus 4? 2. It's as easy as that. Degrees are tied, ratio of the leading coefficients. It's a very well-behaved function, no stressing about plus or minus. How about letter B? What would the limit be as n goes to infinity of a sub n? Because? Bottom wins. Good. No stress about plus or minus because number 1 is well-behaved and number 2, 0 is 0 is 0. No stress. How about the third one? 1/2. Once again, well-behaved. All three of these, the sequences converge. All three of these, the sequences converge. The series would actually diverge on the top and bottom one for sure, and the middle one would also diverge. The series diverge on all three. But the sequences converge on all three, so go team. The only time the sequence won't converge is if, once again, your sequence is bouncing back and forth between oscillating values, or if they go to infinity or negative infinity. Kiddos, you should have already written this down. Do tomorrow. As I check and see if anybody has any questions on 12.4, if you already started it, if my smartboard works, goodness gracious. The final section of chapter 12, which we are going to finish up tomorrow. Section 12.5. Let's start off class just by getting this written in, okay? Can I show it all? Yeah, let's show it all. All right, I'm going to freeze the screen. If anybody did start homework, does anybody have any questions they got stuck on in homework over the weekend, 12.4? I think I covered most of the tricky things that could happen. Okay. Then I'll unfreeze and let you guys keep writing. Section 12.5, you guys remember from the preview of calculus, I said there were two big problems. One of them was a tangent line problem. That was 12.3. Slope of a tangent, have to define a derivative. That's that whole limit of a difference quotient thing. And ooh, there are those basic rules. rules. Those are nice. Well, basic rules. We've learned one, kind of two. But anyway, there are lots more. But section 12.5 says, okay, now that you've talked about limits to infinity, you're ready to at least kind of go a little deeper into the area problem. But to do the area problem, if you can remember, there was this curvy area under a function. There was no geometric formula to help us find that area. And since there was no geometric formula to find that area, instead we wrote rectangles. And if you fit in 3 or 4 or 5 rectangles, yeah, it'd be a fairly good approximation. But then we're like, what if you fit in 10 or 20 or 50 or 100 or 1,000 or 1,000,000? What if we let the number of rectangles approach infinity? Limit. Approach infinity and add them all up. Summation. We'll have to review a couple things to get here. John?
Is that a comma or no?
Comma. Comma. The sum is equal to this formula such that, or when, or for the values of r that are less than 1. Remember, for infinite geometric series, they only converged if the common ratio was in between 1 and -1. That's what this is saying. That formula only works if r is in between 1 and -1. And to be honest, this is something that we've already seen because this, or for this, I already showed you this notation because I said, hey, guess what, guys? As long as the common ratio is someone in between 1 and -1, this little piece, as I take the limit, is going to approach what? 0. And since it approaches 0, I'm able to arrive at my a sub 1 over 1 minus r as my limit. And maybe some of this makes a little more sense now that you've done it. If you guys want to, you could also add in, this is just shortcut notation for r between 1 and -1. Goal for tomorrow. Do what? Homework, limits to infinity and beyond. Checking your degrees as a shortcut, that's totally fine, but beware the pluses or minuses, the nasty square roots, and absolute values. Bye, guys.